Hello, this is Mr. Ruby, and this is Newton's second law, a reading of the textbook with interesting side notes as I talk about it. Force and acceleration. When you go shopping in a grocery store and push a cart, you exert a force to make a cart move. If you want to slow down or change the direction of the cart, a force is required to do this as well. Would it be easier for you to stop a full or empty grocery cart suddenly, as in Figure 7? When the motion of an object changes, the object is accelerating. Acceleration occurs anytime an object speeds up, slows down, or changes direction of motion. Newton's second law describes how forces cause objects' motions to change. Newton's second law of motion connects force, acceleration, and mass. According to the second law of motion, an object acted upon by a force will accelerate in the direction of the force. The acceleration is given the following equation. Acceleration is net force divided by mass, or acceleration is force net divided by mass. In this equation, A is acceleration, the M is mass, the F is the force, or the net force. If both sides of the above equation are multiplied by the mass, then the equation can be written this way, which is what we'll do. Force equals mass times acceleration. What is Newton's second law? Force equals mass times acceleration. Or if we look at the grocery cart here, you have the lady with the less full and the young lady with the more full grocery cart. So the more mass an object has, the more force it takes to change its acceleration. Units of force. Force is measured in newtons, abbreviated with a capital N, because the SI unit for mass is the kilogram, and acceleration has units of meters per second squared. 1 newton is also equal to 1 kilogram meters per second squared. In other words, to calculate the force of a newton from the equation shown in the prior page, the mass must be given in kilograms and the accelerations in meters per second squared. Usually what we do is just write it as so many newtons, 10 newtons, 20 newtons, that type of thing. Let's talk about gravity. One force that you're familiar with is gravity. Whether you're coasting down a hill on a bike or a skateboard or jumping into a pool, gravity is at work pulling you downward. Gravity is also the force that causes Earth to orbit the Sun and the Moon to orbit the Earth. But what is gravity? The force of gravity exists between any two objects that have mass. Gravity always is attractive and pulls the objects towards each other. A gravitational attraction exists between you and every object in the universe that has mass. However, the force of gravity depends on the mass of the objects and the distance between them. Gravitational force becomes weaker the farther apart an objects are, and also decreases as the mass of the objects involved decreases. So the farther apart, or the lower the mass, the less gravity. For example, there is gravitational force between you and the Sun, and you and the Earth. The Sun is much more massive than the Earth, but it is so far away that the gravitational force between you and the Sun is too weak to notice. Only Earth has enough mass and is close enough to exert noticeable gravitational force on you. The force of gravity between you and Earth is about 1,650 times greater between you and the Sun. Let's talk about weight. Weight. The force of gravity causes all objects near Earth's surface to fall with an acceleration of 9.8 meters per second squared. By Newton's second law, the gravitational force on any object near the Earth's surface is force equals mass times acceleration, which is 9.8 meters per second squared. A gravitational force also is called the weight of the object. Your weight on Earth is the gravitational force between you and Earth. Your weight would change if you were standing on a different planet other than Earth, as shown in Table 1. Your weight on different planets is the gravitational force between you and the planet. So on Mars, you're only 38% of your weight from Earth. On Jupiter, you'd be 236%, so twice as much. On Pluto, you'd be only 7/10 as much. Figure 8. Weight and mass. Weight and mass are different. Weight is a force, just like a push of your hand is a force, and is measured in newtons. When you stand on a bathroom scale, you are measuring the pull of Earth's gravity, a force. However, mass is the amount of matter in an object, and it doesn't depend on location. A book with a mass of 1 kilogram has a mass of 1 kilogram on Earth or on Mars. However, the weight of the book would be different on Earth and Mars. The two planets would exert different gravitational force on the book. So remember that. The mass isn't changing, but the weight may. Using Newton's second law. How does Newton's second law determine how an object moves when acted upon by forces? The second law tells how to calculate the acceleration of an object if mass and the forces acting on it are known. You may remember that motion of an object can be described by its velocity. The velocity tells how fast an object is moving and in what direction. Acceleration tells how velocity changes. If the acceleration of an object is known, then the change in velocity can be determined. Speeding up. Think about a soccer ball sitting on the ground. If you kick the ball, it starts moving. You exert a force on the ball, and the ball accelerates only while your foot is in contact with the ball. If you look back at all the examples of objects speeding up, you'll notice that something is pushing or pulling the object in the direction it is moving, as in figure 8. Right here we have two people going down over the hill, applied force pushing in the direction that it's going in. The direction of the push or pull is the direction of the force. It's also the direction of the acceleration. Calculating acceleration. Newton's second law of motion can be used to calculate acceleration. For example, suppose you pull a 10 kilogram sled so that the net force on the sled is 5 newtons. The acceleration can be found as follows. Okay, this formula here. The sled keeps accelerating as long as you keep pulling on it. The acceleration does not depend on how fast the sled is moving. It depends only on the net force and the mass of the sled. Slowing down. If you want to slow down an object, you would have to push or pull it against the direction that it is moving. An example is given in figure 9. Here, the force opposite of the velocity in the direction of the motion. Suppose you push a book so it slides across a tabletop. You exert a force on the book when your hand is in contact with it, and the book speeds up. Sliding friction also acts on the book as it starts to move. After the book is no longer in contact with your hand, friction acts in the opposite direction to the book's motion. This causes the book to slow down and come to a stop. Here's a math problem, practice problem if you'd like to figure that out. Turning. Sometimes force and motion are not in a straight line. If the net force acts on an angle to the direction of an object it's moving, the object will follow the curved path. The object might be going slower, faster, or at the same speed after it turns. For example, when you shoot a basketball, the ball doesn't continue to move in a straight line after it leaves your hand. Instead, it starts to curve downward, as shown in figure 10. The force of gravity pulls the ball downward. The ball's motion is a combination of its original motion and the downward motion due to gravity. This causes the ball to move in a curved path. So the ball is released, and it's going the direction of the force applied to it with the push, but gravity is pulling it at the same time. So it goes here to the peak, and then it hits right for the hoop. but gravity pulls it down. That's why you get that nice arc. Circular motion. A rider on a merry-go-round ride moves in a circle. This type of motion is called circular motion. If you are a circular motion, your direction of motion is constantly changing. This means you are constantly accelerating. According to Newton's second law of motion, if you are constantly accelerating, there must be a force acting on you the entire time. Think about an object on the end of a string whirling in a circle. The force that keeps the object moving in a circle is exerted by the string. The string pulls the object to keep it moving in a circle. The force exerted on the string is the centripetal force and also points toward the center of the circle. In circular motion, the centripetal force is always perpendicular to the motion. You can try this sometime with a cup of water and a string. If you spin it fast enough, you can keep the water in the paper cup. Satellite motion. Objects that orbit Earth are satellites of Earth. Satellites go around the Earth in nearly circular orbits, with the centripetal force being gravity. If gravity is pulling satellites towards Earth, why doesn't a satellite fall to Earth like a baseball does? Actually, a satellite is falling to Earth just like a baseball. Suppose the Earth was perfectly smooth with no mountains, hills. Imagine you throw a baseball horizontally. Gravity pulls the baseball downward so it travels in a curved path. If the baseball is thrown faster, the path is less curved and it travels farther before it hits the ground, as shown in figure 11. If the baseball were traveling fast enough as it fell, its curved path would follow the curve of the Earth's surface. Then the baseball would never hit the ground. Instead, it would continue to fall around the Earth. Satellites in orbit are being pulled to Earth just as baseballs are. The difference is that satellites are moving so fast horizontally that the Earth's surface curves downward at the same rate that the satellites are moving downward. The speed at which an object must move to go into orbit near Earth's surface is about 8 kilometers per second, or about 29,000 kilometers per hour. To place a satellite in orbit, a rocket carries the satellite to a desired height, and then the rocket fires again to give the satellite horizon speed it needs to stay in orbit. Air resistance. Whether you are walking, running, biking, air is pushing against you. This push is air resistance. Air resistance is a form of friction that acts to slow down any object moving in the air. Air resistance gets larger as an object moves faster. When an object falls, it speeds up as gravity pulls downward. At the same time, the force of air resistance pushing up on an object is increasing the object's moving faster. Finally, the upward air resistance force becomes large enough to equal the downward gravity force. When the air resistance force equals the weight, the net force of the object is zero. By Newton's second law, the object's acceleration then is zero, and its speed is no longer increasing. The constant speed of a falling object reaches when the air resistance balances the force of gravity is its terminal velocity. So you drop something, and air resistance pushing back against it, slowing it down, and at some point it will not speed up anymore, and it will equal the pressure of the air resistance pushing back on it. Air resistance shape. We've got some skydivers here. The amount of air resistance depends on the object's shape, as it depends on what speed is. Moving at the same speed, the air resistance on a pointed, narrow object is less than on a broad, flat object, such as a leaf or a piece of paper. Ooh, there's a clue, a piece of paper. A falling skydiver is a spread eagle position, as shown in figure 12. Excuse me. Might reach a terminal velocity at about 200 kilometers per hour. But with its arms stuck backward, and legs closed, the air resistance is less, and the skydiver might reach a terminal velocity of over 300 kilometers per hour. When the skydiver opens the parachute, the force of air resistance on the open parachute is so large that the skydiver's terminal velocity quickly reduced to about 20 kilometers per hour. And that's our reading. Let's go through some of the highlights. Once again, Newton's second law. Keep in mind that an object is accelerating depends on the mass and the force on the object. More mass takes more force to change the acceleration, as this girl crashes into all these grapes. The unit of force is the Newton right here, newtons, which is 1 kilograms per second squared. Gravity, everything has gravity. Gravity is pulling on each other. The important part about gravity is to remember that gravitational force becomes weaker the farther apart the objects are, and also decreases the mass of the objects involved. Decrease. Weight is just a measure of gravity pulling on you. So weight can vary by location, but mass does not. So calculating acceleration is force times mass equals acceleration. Force due to gravity, remember gravity is pulling on things. Circular motion, centrifugal force. If you could throw a ball fast enough, it could go all right around the Earth. So satellites in orbit, they're not really weightless. It's more that they are in free fall. They are always falling around the Earth when it's in orbit. Air resistance, remember this, terminal velocity. When something is dropped, it can only speed up so fast before the air resistance pushing back against it will slow it down. Air resistance is like friction. If you're riding in the car at 40 or 50 miles an hour, stick your hand out the window, you can feel that air resistance pushing against your hand. That's kind of the same concept. Skydiving, shape makes a difference. So here's an experiment. Take 2 pieces of paper, crumple one up, leave one flat. You drop them at the same time. The crumpled one will hit the floor first, and the flat one will just kind of float down. And that has been the textbook reading going over of Newton's second law. Thanks for joining me. This is Mr. Ruby, and have a nice day.